In this section, we will review the effect on calibration from a detector's lack of sensitivity. According to R.P.W. Scott, in a discussion of gas chromatography detectors, detector sensitivity, or minimum detectable concentration, is defined as the minimum concentration of solute passing through the detector that can be unambiguously discriminated from the noise. The size of the signal that will make it distinguishable from the noise, the signal-to-noise ratio, is an arbitrary choice. It is generally accepted that this electronic measuring instrument's discrimination is possible when the signal-to-noise ratio is 2, and this criteria has been adopted for chromatography detectors. While the qualitative identification of a peak may be at a signal-to-noise of 2 to 1, the signal-to-noise required to accurately quantitate a response is higher. In the article, How to Choose an ELS Detector, it is stated that the limit of quantitation, or LOQ, is the lowest concentration of an analyte in a sample that can be determined with the acceptable precision and accuracy using the operational conditions of the method. The LOQ is usually defined as a signal-to-noise ratio of 10 to 1. In a document published by Perkin-Elmer, the detection versus quantitation level issue is discussed for ICP analyses. It says, measurements made at or near the detection limit, however, are not considered to be quantitative. For quantitation, plus or minus 10%, it is recommended that an element's concentration should be at least 5 times higher than the detection limit. For accurate quantitation, plus or minus 2%, the concentration should be greater than 100 times the detection limit. Some of the newer EPA methods are also setting limits for the signal-to-noise required for detection. In EPA method 515.3, it states, the EDL, or estimated detection level, is defined as either the MDL or a level of a compound in a sample yielding a peak in the final extract with a signal-to-noise ratio of approximately 5, whichever is greater. In EPA methods 515.4 and 532, the EPA has written similar statements stating that the MRL is the threshold concentration of an analyte that a laboratory can expect to accurately quantitate in an unknown sample. The MRL may be established at an analyte concentration either greater than 3 times the MDL or at a concentration which would yield a response greater than a signal-to-noise ratio of 5. In a discussion in How to Choose an ELS Detector, it describes how to calculate the signal-to-noise ratio. This will be shown over the next 3 slides. This first slide states, it is important to use a peak height measurement instead of a peak area measurement when looking at minimum detection levels because tailing or fronting peaks are difficult to accurately measure at lower concentrations. Signal-to-noise ratios are easiest to determine by printing the chromatogram and using a ruler to measure both the noise and the signal. And finally, to calculate the signal-to-noise ratio, measure the peak height in millivolts and divide by the normalized noise value. It is further stated that the detector noise is measured by constructing 2 parallel lines embracing the maximum and minimum signal over the defined time period. The normalized noise level, or ND, is calculated by taking the distance between the parallel lines measured in millivolts, which is the measured noise, or Vn times the attenuation factor, or A, and finally dividing this by the amplification factor, or B. In this example from a lab's EPA 8260 calibration data, the analyst inappropriately manually integrated the lowest two standards gathering noise for vinyl chloride where no peak with a ratio of 2:1 is present. The next highest standard, the 5 part per billion standard, finally was showing a response above the noise with a signal-to-noise ratio of about 4:1. This is an example of how to get a rough estimate of the signal-to-noise ratio without performing the calculations shown in the previous slides. While the signal-to-noise ratio is finally at a level to quantitate, the analyst has still questionably manually integrated the peak. The analyst, however, used the 1, 2, and 5 part per billion standards in the calibration curve. Vinyl chloride in the EPA 8260 method is a CCC, or calibration check compound, which must have a relative standard deviation of less than 30% for the curve. This calibration curve plot that contains the 1 and 2 part per million standards that did not have adequate signal-to-noise ratios of over 2:1 and were inappropriately manually integrated gave an acceptable appearing relative standard deviation of 21.7%. The analyst, however, should never have included the data for the two lowest standards. In this example of two compounds from EPA method 552 analyses, the two lowest standards are approaching the laboratory's level of detection. When quantitating standards or samples near the level of detection, high levels of inaccuracy and deviation are encountered. In both of these compounds, the second to the lowest standard is actually calculating to have a response ratio lower than the lowest standard. In both cases, the lowest standard should have been eliminated. This inorganic example of an ammonia analysis on a latchet system shows the same sensitivity problem as just mentioned on the previous slide with the 552 analyses. The second lowest, or 0.02 part per million standard, has less response than the lowest standard at 0.01 part per million. However, when the calibration plot is observed, the R value is 0.99989 and appears to be acceptable, even though the 0.02 part per million standard has less of a response than the 0.01 part per million standard.